Hey guys, we're solving this chemistry paper today. This is chemistry paper 4, May-June 2022, paper 4.1. So paper 4.1 was actually the same as paper 4.3. They're the same variant. You can match these, they're the same variant, okay. So before we start, let's take a look at the threshold. So for paper 4.1, the maximum raw mark available was 100, right? So 4.1 and 4.3 had the same threshold. A was at 59 and B was at 50. So out of 100, A was at 59 and B was at 50. And what else? C was at 41. 41, 31, 20. 41, 31, and 20. Okay. 41, 31, and 20. So this was the threshold. I mean, it's fine. It's okay. So think of it like this: when you're gonna give your exam in the major 2023 series, basically assume that A will be at 60. Okay, that's an easy bet, and A star is at around 75 to 80. Okay, usually. So if you're aiming for an A star, you need to get an 80 out of 100 at least, then you're safe. All right, so let's begin. A lot of you have been requesting this paper. I was too busy to solve it actually. I'm gonna do paper 4 too as well afterwards. So let's go. The solubility of group 2 sulfates decreases down the group grade. So this is a very common question. We are used to this. So it's a 3-mark question. The trend is given, we just have to explain it. So we just have to say that del H lattice and del H hydration, right, decrease, or both, both of them become less exothermic down the group, right? Or you could say that they become less negative down the group. But a barium sulfate is a white precipitate, right? So what actually happens? You guys do understand that hydration is the factor which actually makes you more soluble. Lattice actually prevents that. Okay, so hydration is actually the dominant factor. It decreases by a greater margin. So you could answer this in 2 ways. You could either say that del H lat decreases or changes less or becomes less exothermic by a smaller extent. Okay, or you could opt for, this is the same point by the way, you could opt for this point over here the other way around. You could say that del H hydration decreases or changes more, or it's the dominant factor. Okay, so this is the second point by the way. Okay, so what about the last point? What is the last point exactly? So the final point is like this. You have to say that therefore del H sol, this is the ultimate factor. If del H sol is more exothermic, it means that the salt is more soluble. So since it becomes less soluble, that means it is more endothermic now. Okay, so del H sol becomes less exothermic, or you could say that it becomes less negative. Same thing. What else? Or you could say that del H sol becomes more endothermic, okay, or more positive compared to before. Or you could talk about the equation itself. You could say that del H so is equal to del H hide minus del H lat. So this is the main equation. Now we know that this is also negative and this is also negative, but there is a minus sign in front of here. So what does this become? Negative and positive. So we want the whole thing to be negative for this to be soluble. Just like Gibbs free energy, right? It has to be negative for the reaction to be feasible. So if the magnitude of this value is greater than this value, right, then it will be negative and soluble. However, if lattice has a higher magnitude than hydration, the total value will be positive, which is why it becomes insoluble. That is exactly what happens to sulfate standard group, because both of them decrease in magnitude. It's just that, you know, basically they become, suppose they were, you know, for example, yeah, they decrease in magnitude, or we could say that they just become, both of them become less exothermic. It's just that, suppose, like initially, if we talk about magnesium sulfate, right, I'll give you an example. Suppose del H hydration is, you know, minus 50 and del H lead is plus 40. So we get a value of minus 10, which is soluble. But when you go to barium sulfate, both of them will decrease, okay? Suppose the hydration enthalpy becomes minus 30, right? It has become less native, okay? But on the other hand, you remember that this was minus 40, right, initially? But there was a minus sign in front, which is why it's minus 50 plus 40, which is minus 10. So that one actually decreases by a smaller margin. What do I mean by that? Suppose it becomes minus 45. Now what? Minus 30? Sorry, minus 35, yeah? Minus 30 plus 35. We get a value of plus 5. So do you see what happened exactly? Like hydration decreased by 20, but lattice decreased by 5. That's the gist basically. Hopefully you guys got clarification. So del H equals to del H hide minus del H lad, and you have to say that, you know, the reaction becomes less exothermic. Basically what I explained to you guys. So these are part of the third point, by the way. So you have to write this point, you have to write this green one or this orange one, and then you have to write any one from these 3 4 sulfates. Now if you were talking about hydroxides, the answer would be the same. In what sense? The first line would be the same, then the second line would just be inverted, and the third line would be del H salt becomes more exothermic. Get it? Describe what is observed when magnesium and barium react separately with excess disulfuric acid. So barium sulfate is a white PPT, okay. So mainly the metal reacts with the acid, so we're gonna get effervescence hydrogen gas. So we are going to see fizzing, obviously, and white precipitate, right, or a white solid forms. Basic chemistry from S, and here we are just going to see fizzing, but magnesium sulfate is actually a soluble salt, so we wouldn't see a white precipitate. Let's find out the KSP. Oh, the KSP of barium sulfate is given at this value. So we know that BaSO4 is basically, you know, breaks down to form Ba plus SO4 2 minus, partially soluble. So the KSP of barium sulfate is actually Ba2 plus multiplied by SO4 2 minus, okay. So basically these two have the same concentration, right? So what do we need to find? We need to find out the solubility of barium sulfate in gram per 100 cm cube. Okay, so guys, the value of KSP is equal to 1.08 times 10 to the power minus 10. Now basically what you guys need to understand is that since it breaks down to form this, the value of this is x, the value of this is x as well, because the molar ratio is 1:1. So can't we write that x square is equal to 1.08 into 10 to the power minus 10? This x is basically the solubility of barium sulfate. Okay, this x is basically the solubility of barium sulfate. Now what? X is equal to root over 1.08 times 10 to the power minus 10, and we get a value of 1.04, right? X is equal to 1.04 into 10 to the power minus 5 mole per dm cube. Now we gotta convert this mole per dm cube to gram per 100 cm cube. Okay, so let's do that. Okay, how? So moles, we know that mass equals to moles times mr. So the mr of barium sulfate, we can use, check that from the periodic table. It's going to be 233.4, but how though? Where is it? So yeah, barium is, here you go, 137.3, sulfate 32.1. Okay, so do it, 137.3 plus 32.1 plus sulfate 04, right? 16 times 4, that's 64. That gives a value of 233.4. Okay, 233.4. Okay, so solubility in gram per 100 cm cube is actually equal to 1.04 times 10 to the power minus 5. Okay, times 233.4, that's converted to grams. Now you guys know that this value is in 1 dm cube. 1 dm cube basically means 1000 cm cube, right? But we need the answer in 100 cm cube. Okay, do you understand? So how to do that? So basically the logic is, if in 1000 cm cube you have this value, okay, if in 1000, in 1 dm cube, which is 1000 cm cube, we have this value. Okay, so in 100 cm cube, we will have 1.04 into 10 power minus 5 times 233.4 divided by 1000 times 100. So that's basically divided by 10. Do you guys get what happened? It's basically a unitary method. So I get a value of 2.42 into 10 power minus 4. Okay, understood? There we go. Next one, we have a Born-Haber cycle. So calculate the standard enthalpy of formation of the sulfate ion. Okay, great. It might be helpful to draw a label during your cycle. By the way, guys, you don't have access to the data booklet anymore starting this year 2022. So all the information you need will be given in this table, but you don't have to use all of it. Okay. So let's begin, guys. Okay. The equation for the formation of a gaseous sulfate ion is shown. All right. So to make barium sulfate, we need barium, sulfur, and oxygen. Okay. Let's do this. So we are starting with barium solid. We are starting with sulfur solid. We are also starting with oxygen gas, but 2 molecules of it, right? So this can directly form BaSO4, right? That is your del H formation. That's the enthalpy of formation. This one, -1473. So that's one route. What is the other route? The manual way, using lattice enthalpy. We can convert barium to Ba plus followed by Ba2 plus using these two. Okay, we can turn it to Ba2 plus, and at first we need to atomize barium. Okay, because barium exists as a solid, you need to turn it into a gas first. So this is step 1, and these are 2 and 3. So you convert barium to a gas. Okay, fine. Sulfur solid plus 2O2. Why don't I draw the diagram here? I think it's gonna be better for you guys, right? Okay. So I convert barium to a gas, then I convert it to Ba2 plus gas. Okay. Sulfur solid plus 2 oxygen gas. Okay. So this is basically del H atomization of barium, and this is basically del H IE 1 plus 2 of barium gas. Okay. Now what? So basically we need 1 sulfate anion. Okay, so you don't really need this stuff. They give you these to trick you because you directly have it. This is the formation of the sulfate anion, right? So can't you do this? Because using these two, we are going to form Ba2 plus a gas plus the sulfate anion. Okay, so this is del HF of sulfate. Okay, that's all. And then we can go for this step, which is the del H lattice enthalpy of barium sulfate. So if you just follow the arrows, if you focus, there are two routes. There is one direct route over here, or there is the detour. So if you add those routes up, they're going to add up. Okay, so atomization of barium, how much is that? Plus 180 plus the first and second IE of barium plus 503 plus 5965. Then we are going to form the sulfate anion, um, oh, which we don't know, plus del HF sulfate, right? Then we have the lattice enthalpy of barium sulfate, which is -2469, and that is actually equal to the enthalpy of formation, which happens to be 147 -1473. So hopefully this makes sense, guys. Could you understand? So del H formation is equal to -1473 -180 -503 -965 plus 2469. Which gives you a value of -652. Okay, moving on. Explain how the lattice energy of barium sulfate differs from cesium sulfate. So they have the same anion. So remember, how do cations affect lattice enthalpy? Mainly depends on the charge, right, and the size. It is proportional to charge, the lattice enthalpy, but inversely proportional to size. So basically it is proportional to charge density. Barium has a higher charge since it's in group 2, just 2 plus charge. Cesium has +1, it's in group 1. Also, it has a smaller size, so it has greater charge density, so it would be higher of magnitude or more exothermic basically. Okay, so BaSO4, the lattice enthalpy of BaSO4. Okay, the lattice enthalpy of BaSO4 is more negative. This is the best wording, or you could say that it's bigger. Very vague. Why? As Ba2 plus is smaller, or you could say that because it has a larger charge, so there is a stronger force of attraction between the ions. So in the previous mark scheme, like if you're 2 out of 3, you'd get 2 marks, okay? But recently you have to read all 3 to get 2 marks and 2 to get 1 mark, okay? So please learn from this mark scheme and please follow this mark scheme. This is the way to go, okay? The reaction of solid hydrated barium hydroxide with amino salts is endothermic. Calculate the minimum temperature at which the reaction becomes feasible. So remember guys, a reaction becomes feasible when del G is 0, okay? And if it turns negative, it is feasible, but the moment it turns 0, it's at the edge of being feasible. Could I clarify? So what's the formula? It's del G is equal to del wait, is equal to del H minus T del S, right? So when it starts to become feasible, you got to say that del G is actually, 0. So we can say that del H minus T del S is equal to 0, or del H is equal to T del S, okay? Or what can we say? We can say that T is equal to del H divided by del S. Now the units will never match in this math, okay? So T is equal to, you got to convert to the same unit, okay? So basically converted to kilojoules, okay? That's the thing that they do in the mark scheme. So this is plus 132 kilojoules. Okay, wait, let me show this. Kilojoule per mole, and this one will be 0 0.616 kilojoule per Kelvin per mole. So think about it, we can get rid of these two units and we end up with the final answer of T is equal to 214.3 Kelvin. Now we need the answer in degrees Celsius. So what do we have to do? We need to subtract 273, right? So that gives us an answer of minus 58.7. Okay. So I'm going to do it 132 by 0.616. Perfect. Degrees Celsius. Awesome. Let's keep on going. You guys are doing great. If you're totally new to A2 Chem papers, I just suggest watch this paper. Watch me solve it. Watch my specimen paper 4. Watch my February March 2022 paper. Watch this paper and watch the 4.2 paper as well when it's uploaded. Okay, I'll try to do more paper 4s, but they don't get very high reach compared to paper 1 videos. So I'll try my best. Plus, they're really time consuming to do, and they're really hard to do as well compared to paper 1. Okay, so I'd appreciate some support from you guys. It would make me motivated to work harder for you. Anyway, good luck with your exams. So yeah, if you do like the content, please subscribe to the channel and like the video. So let's look at the next one. We have another reaction where barium hydroxide reacts readily with ammonium chloride on mixing at room temperature. Okay, so we have some info. Calculate the standard Gibbs free energy. Okay, great. So we know that del G is equal to del H minus T del S. Yeah. So we have the temperature. It's 25 degrees Celsius plus 273, 298 Kelvin. We have del H. We have to find del S. So del S, the answer is actually S of products minus S of reactants. Okay, so let's do this. So what are the products here? 2NH3, 1 BaCl2, 2H2, 1 8H2. Okay, so that's product, product. Okay, so 192 times 2 plus 203 plus 70 times 8. Is that okay? So this is one part. This is the product part. What about the reactants? 2 NH4Cl and one of this. So 95 times 2 plus 427. So what value are we getting afterwards? Plus 530. Mind the unit, joule per Kelvin per mole. As usual, you got to convert this to kilojoule again. Okay, so del H, it's in kilojoules. So that's plus 133. Why do I say kilojoule? Because the final answer is in kilojoule as well. The SI unit of Gibbs free energy and enthalpy is kilojoule per mole, but the SI unit of entropy is joule per Kelvin per mole. Okay, so minus the temperature needs to be converted to Kelvin. So 25 plus 273, which is 298 times 530 by 1000, which is 0.530. Okay, so yeah, if you do solve this, you get an answer of minus 24.9 kilojoule per mole. Awesome. Great. Let's move on to the next one. I really need to sleep soon, so I'm going to record the rest of this later. Let's see how long we can go. So for question number 2, they want us to define a transition element. So what is a transition element? It is basically a D block element. Okay, transition element is a D block element which forms one or more stable ions, compounds, oxidation states, okay, with partially filled 3D orbitals, or you could say shells or D subshells. So yeah, you don't need to mention the 3 by the way, it was optional, so just any D orbital works. Draw the shape of the 3 dz square. Okay, so you guys know that there's xy, xz, zx, x square minus y square, and z square. So it is basically a pz orbital. That means the orbital is a dumbbell shaped orbital which passes through the z-axis, literally passes through it like a skewer. And what else do we have? We have a halo. Okay, we have a halo which is like this basically. Is that clear? We have a halo like this which passes along the plane of the x and y axis. Okay, that's your answer. Manganese 4 oxide amino 2 acts as a heterogeneous catalyst in the decomposition of hydrogen peroxide. Great. Explain what is meant by heterogeneous catalyst. So basically the catalyst is in a different phase compared to the reactant. Okay, so it's a solid essentially. So the catalyst and the reactants are in a different state or phase. Okay, phase is the better word by the way, just like in Haber process and contact process, right? Iron and vanadium pentoxide. Describe the mode of action of a heterogeneous catalyst. So I'm seeing this question after a very long time, by the way. It's mainly by adsorption, right? So what happens is adsorption of reactants to the surface of the catalyst. Okay, so that's the first step. Now bonds in the reactants weaken. Okay, lowering the activation energy. So next what happens is the reaction occurs and the products are desorbed. Okay, so this is what you're gonna write. So for example, in the Haber process, nitrogen and hydrogen, they come close to the surface of iron by diffusion and then they're adsorbed. Adsorption is basically sticking, not going into the object. Then the bonds between nitrogen and broken as new IMFs are formed between nitrogen and nitrogen and iron, hydrogen and iron. Then the new product forms, okay, and they desorb finally. Okay, so Mn2O7 can be made by treatment of KMnO4 with concentrated sulfuric acid. Okay, so let's try that. Let's try to construct these equations. Let's try. Okay, so KMnO4 will react with H2SO4 to form this compound basically Mn2O7. So we need two of this minimum. So clearly the salt will be potassium sulfate. Okay, so you guys need to figure this out. Okay, because there's no other option. So the salt is K2SO4. So yeah, we needed 2 potassium. Now how many oxygens do we have on the left hand side? 2 4 is 8, 8 plus 4 is 12. I've already used up 7. Okay, I've already used up 7, but I need to use up 12. So I'm missing 5. Oh wait, I have 7 here and 4 here. That's 11. So I just need one more. So that's 1 molecule of water. Is that fine, guys? It matches, right? I would go for this, honestly. But the mark scheme gave you an alternate answer, if you're wondering. You could also write this 2KMNO4 plus 2H2SO4 gives you Mn2O7 plus H2O plus potassium hydrogen sulfate. Same. It's okay. It's up to you guys. Next, what's the second reaction? In this second one, Mn2O7 decomposes readily, so nothing else reacts with it to form a manganese 4 oxide. Okay, MnO2, this one, manganese 4 oxide, right? And occurs diatomic gas. Okay, let's see what diatomic gas we get. So next step, Mn2O7 decomposes readily to form MnO2. So we need 2 to balance this minimum. Okay, so I've used up 4 oxygen. I have 3 oxygen remaining. So the only possible colorless gas being formed is oxygen, since we don't have any other possible element. And we need 3 atoms of oxygen, so we need to give a 3 by 2 over here. Does that make sense, guys? Is that clear? Okay. Okay then. So in E we have aqueous manganese 2 ions which show similar properties to aqueous copper 2 ions when reacted separately with NaOH aqueous and concentrated HCl. So we know that copper 2 ions actually form a pale blue precipitate with sodium hydroxide and a yellow solution with concentrated HCl, right? So they're saying that manganese behaves in the same way. So let's try to do this. The ionic equation for manganese with NaOH. So compare it with copper. This is copper. Okay, so this is basically copper, CuH2O6. 2 plus, it basically reacts with 2 OH minus to form copper hydroxide, CuOH2 solid, and we release 6 moles of water. So this equation will actually be the same. Okay, so it's manganese followed by H2O6, and yeah, this has the charge of 2 plus. This reacts with 2 hydroxide ions aqueous, and it's going to form manganese OH2 solid plus 6H2. So what type of reaction is it? Since we're getting a precipitate, the best answer would be precipitation. The type of reaction is precipitation. You could also say that it's an acid-base reaction because water is being formed as it's reacting with hydroxide. Or you can call it deprotonation. Okay, deprotonation, because yeah, protons are being lost. Basically, water is being lost from manganese, but yeah, you could call this a deprotonation reaction. On the other hand, copper from CuCl4, so manganese will do the same thing. So let's do this. MnH2O 6 2 plus CuCl4, right? So with 4 chloride anions, this actually forms MnCl4. So plus 2 minus 4, that's 2 minus, the charge is 2 minus, and yeah, 6 molecules of water will be released. This is a 6, by the way. It is a 6. What is the type of reaction? So what happened? Chloride just took the place of water. One ligand took the place of another. So this is in fact a ligand exchange reaction, or it's a substitution reaction, or replacement. First time I'm seeing this, or displacement. This is a common answer. It's a displacement reaction. Moving on, from now onwards you won't have access to the data booklet, so you have to use the values given here. So is the formula of the manganese species formed when Mn2 plus reacts with chlorine. So chlorine is an oxidizing agent, so chlorine will be oxidized. This is actually the reduction potential of chlorine. So the oxidation potential of chlorine will be the opposite. It will actually be minus 1.36. Okay. But you guys know that we don't need this actually, because chlorine is an oxidizing agent. So that means that it will be reduced in the process. Okay. So on the other hand, Mn2 plus, this is the reduction potential of manganese, right? Or the oxidation potential of manganese. This is the reduction potential of Mn2 plus or the oxidation potential of Mn. So we don't really need this equation, because if Mn2 plus is gonna be oxidized, it's gonna go further, because chlorine can't be oxidized, right? Usually it can. Okay, you know that in HOCl chlorine actually has an oxidation number of +1, and it can go to +5 in NaClO3, remember? So we have to check here. Okay, we have to check here like what is possible. So for example, I am assuming that chlorine will be reduced. Okay, so I'm going to take the reduction potential of chlorine. On the other hand, I'm going to assume that manganese 2 plus is going to be oxidized to MnO2, where the oxidation number of manganese is +4. So since this is the reduction potential of MnO2 to Mn2 plus, the oxidation potential of Mn2 plus will be minus 1.23. So check that out, plus 1.36 minus 1.23, that gives you a value of 0.13. Yeah. So let's check whether it goes further. So this is MnO4 minus and this is MnO2. So the reduction potential of MnO4 minus is 1.67. So the oxidation potential will actually be minus 1.67. So let's try again. Plus 1.36 minus 1.67, that's a negative value, so that is not feasible. Okay, so that's minus 0.31, it won't happen. So the final product is actually MnO2. Okay, this product over here, and the type of reaction is obviously a redox reaction. By the way, you guys could think that why isn't chlorine being oxidized, if you wanted to try that. Okay, just in case. So this is the oxidation potential of this is the oxidation potential of chlorine. So the reaction potential, so oxidation potential is minus 1.64, and the reaction potential of manganese is minus 1.18. So Mn2 plus basically. So minus 1.18 minus 1.64, that's a negative value. Okay, so here Mn2 plus cannot be reduced and chlorine cannot be oxidized. Okay, moving on to question number 3. The rate of reaction between 2-chloro-2-methylpropane. Okay, so this basically, and methane is investigated. This is basically a tertiary halogen alkane. This is a nucleophilic substitution reaction, and this is SN1. So it's a first order reaction, and rate only depends on the halide because the first step is the slow step. Use the graph to determine the rate at 40 seconds. Okay, so we draw a tangent at 40. Damn, this was hard to do, mainly because this is 25, right? So the midpoint is actually 37.5. Okay, this is 37.5. Oh, so these points are they increase by 10, right? No, not always. 12.5? No, not always. This is 37.5 basically. So 40 should be somewhere over here, approx. So let's try to draw the tangent. Yeah, this is going to be hard to do for me. Something like this basically. Okay, let's check. Wow, this was really hard to do. Or is it like this? Basically, if you make it past 2.15 and 75 over here. Yeah. Kind of, I guess. Kind of. 0.0150 divided by 8-ish. It should be around 1.7 into 10 power minus 4. So yeah, this should be a bit lower. I think the first one was fine. Somewhere around here. Yeah, if you wanted to draw a perfect graph, my first graph was okay actually. It's something like this. Okay. So this is somewhere around 75 plus 100 by 2. That's 87.5-ish. This one, 87.5-ish. And this is somewhere around, you know, maybe 0.10140. A bit steeper. Yeah, so this 1 mark was a hit or miss actually. I actually needed this, you know, I needed a hard copy. Then I could do it better. So 0.0145 divided by 86 or something. Yeah, approximately. Basically, it's 0.0145 divided by 86 or something. That gives me an answer of 1.686 into 10 power minus 4, which can be rounded off to 1.7 into 10 power minus 4. Okay, approx 0.000170 approximately. Okay, so it would be better to do if I had a hard copy with the scale, but it should be around the lines, along the lines of this. If you got 1.6 into 10 power minus 4 or 1.8 into 10 power minus 4, you would still score, full marks. So use the graph to show that the overall reaction is first order. So we can use the half-lives to do that. So the initial concentration is 0.02, half of it would be 0.01. So let's check the time. Approx 30 seconds. Half of this is 0.005, so approximately 60, right? So 30 and 60, so the gap is 30 seconds. So you need to show evidence of the construction lines. You get 1 mark for that, and then you have to say that there is constant half-life, okay, or you can say that there is constant time between halving of concentration. (30 seconds), right? So first order, that is one way to check, right? It differs for zero order or a second order reaction though. In one, the half-life progressively increases, and in the other it progressively decreases. In different reaction, which is also first order, 75% of the reactant is consumed in 320 seconds. Calculate the rate constant K for this reaction. Okay, interesting question. So think about it. In one half-life, if you had an initial concentration of A naught, it would turn into A naught by 2, so that's 50% gone. Okay, and then in second T half, it would turn into A naught by 2 to A naught by 4. Okay, so that is basically half of the second part, but 25% of the initial value, right? So how much did we lose actually? 50% of the initial one in the first time, followed by 25% of the initial concentration. So in total we lost 75%. So basically 75% loss means two half-lives have passed. Okay, so 75% loss, this actually refers to 2 half-lives, okay, in 320 seconds. So 1 T half is actually equal to 1/62. Now we know that for first order reaction, K is equal to ln 2 by K, or T half, sorry. So K is equal to 0.693 divided by 160. Try doing this. 0.693 by 120, sorry, 0.693 by 160, which gives an answer of 4.33 into 10 to the power minus 3. Great. And the order or the unit will be second to the power minus 1, because ln 2 has no units, right? That's all. Define standard electrode potential. Okay, really important. It is the voltage or EMF, or you could say it is the potential difference. Okay, when a half cell is connected to a standard, to an SHE, basically to a standard hydrogen electrode, when a half cell is connected to standard hydrogen electrode. Do you understand? And you obviously have to mention that this is under standard conditions. Under standard conditions, 1 mole per dm cube concentration, 1 atm pressure, 298 Kelvin. Okay. So basically, if you anything in the potential difference of an electrode compared to the standard hydrogen electrode, which is 0, right? So everything is relative to hydrogen, right? Okay, so a Sol bridge is used in an electrochemical cell. State the function of the Sol bridge. So basically, it completes the circuit, essentially, that's one role. Also, it maintains the charge balance. I'll tell you what I mean in a bit, okay? When I draw the diagram below. So it completes the circuit or maintains the charge balance. So ions move from the salt bridge to maintain charge balance, or basically the salt bridge completes the circuit. Okay, to complete the circuit, to maintain charge balance or to complete the circuit. So let's draw this diagram. It's a dichromate 6 and chromium 3 plus half cell against a standard hydrogen electrode. Okay, so the standard hydrogen electrode is a gas electrode. So it's going to be like this. We are going to pass in hydrogen gas at 1 atm pressure, and we need a platinum catalyst. So this is platinum solid, and this is a solution of H plus. One mole per dm cube. Okay. On the other hand, this is a half cell which has 2 ions in 2 oxidation states. So we also need another platinum catalyst. Remember, in gas electrodes and in half cells with 2 ions, you will use platinum as a catalyst. Could I clarify? So we need these 2 ions. What are they? Platinum solid. We need Cr2O7 2 minus aqueous. That's one. And of course it has to be acidified. Okay, as well as Cr3 plus aqueous. You need all 3 over here. And these all have to be in 1 mole per dm cube, and you need to mention that this is at a temperature of 298 Kelvin. Okay, that's the temperature. And you need to label the voltmeter as well. Okay, and the salt bridge has been labeled. So basically the salt bridge is connecting these 2 circuits, or else electricity won't be able to flow. And one of them is going to be oxidized, right? And the other is going to be reduced. So we are going to get a lack of some positive or negative ions on each side. So that will be filled up by the salt bridge. Usually it's made up of potassium nitrate. Label the native electrode and the direction of electron flow. Okay, so basically we know that the standard hydrogen electrode has an electrode potential reduction potential of 0. And this dichromate electrode has an electrode potential of plus 1.33. So clearly, since it has a higher reduction potential, it will be reduced. So the electrode that gets reduced is termed as this side is termed as the cathode. So clearly this side will be the anode. Okay, this side is our anode. Now in an electrochemical cell, okay, this is an electrochemical cell, the cathode is actually positive and the anode is actually negative, in contrast with an electrolytic cell. Here the cathode is positive and the anode is negative. So we know that electrons will move away from the negative side towards the positive side. So since the cathode is positive, electrons will flow towards this side. Okay, so this is the movement, and we need to label the negative electrode. Okay, so this side is the negative electrode. Okay, this one, the standard hydrogen electrode. Is that fine, guys? Okay, let's move on. We don't have access to a data booklet, so all info will be given in the sheet. We have to use this. Table 3.1 lists relevant electrode potentials for some electrode reactions for use in D1 and D2. Ethanol is oxidized to ethanoic acid. Okay, so we have to use this equation, oxidation of ethanol to ethanoic acid, using dichromate in acidic conditions. So using this will be reduced. Okay, so these are our two equations. Cr2O7 2 minus plus 14H plus 6E minus is equal to 2Cr3 plus 7H2O. That's plus 1.33. And we have to use this oxidation potential, so it's actually going to turn into plus 0.94 rather than minus 0.94. And it's going to be CH3CHO plus H2O is actually equal to CH3COOH plus 2H plus 2E. So how are you gonna balance the number of electrons? It's very simple. We have 6 here, so you have to multiply this side with a 3. So if you do that after multiplication with 3, what do you end up with? Wait, I'm gonna write this again. So here you go. This is our end result. Six, 6, and 3, 3. See if you guys understood how I did this. Now I can get rid of these two, right? You can get rid of these 3 over here, and this actually turns into 4. 7 minus 3 is 4. I can get rid of these 6, and this actually turns into 14 minus 6 is 8. And we have our final answer. Okay, so I'm just gonna add them up and write them over here. Cr2O7 2 minus plus 8H plus 3CH3CHO is equal to 2Cr3 plus 3CH3COOH and plus 4H2. How about that? Okay, so that's that. There was an alternate one, like if you decide to write ethanoic acid at CH3COO minus, that would be okay as well. but you don't need that, honestly. Okay, this is the better way to do it. In that method, you just write CH3COH as CH3COO minus. Okay, you basically dissociate this into 3CH3COO minus plus 3H plus. As a result, you could get rid of more H plus. So 3H plus over here and 8 minus 3, 5H plus over there. So that would be your answer. Do you get what I mean? That is not required. You could go for it though. I mean, it's fine, but it's okay. So what's the E cell actually? E cell is equal to plus 1.33 plus 0.94, which happens to be plus 2.27. Do you guys want the alternate answer actually? You got it, right? You're gonna dissociate this part into CH2CO minus and 3H plus. So that 3H plus will be deducted with this 8 plus over here. So you're gonna end up with 5H plus ultimately. And this is gonna turn into 3CH3CO minus. Okay, moving on. This is the new addition to the syllabus actually, which has been added in 2022. This is the new relationship between del G and E cell. So the new equation is del G is equal to minus NF E cell. Okay, is that clear? So del G is equal to minus, we have to see the number of electrons transferred, okay, in this particular equation. So ethanol has been oxidized to ethanoic acid, and we have 2 moles of ethanol. Okay, so ethanol plus oxygen, do you guys understand? So that is here um, ethanol to ethanoic acid. So ethanol does not go to ethanoic acid directly. This is ethanol. Ethanol will turn into ethanol first, then ethanol will turn into ethanoic acid. Could I clarify? Ethanol turns into ethanol first, then ethanol turns into ethanoic acid. So for each mole of ethanol to ethanol, we require 2 moles of electrons, and for each mole of ethanol to ethanoic acid, we require more 2 moles, right? 2 more moles of electrons. So in total, we actually have 4 moles of electrons. Hopefully that makes sense. Is that fine? So the number of electrons here should be 4 in the place of n. And you can also think of it this way: 1 mole of oxygen turns into 2 moles of water, or is reduced to 2 moles of water, and in the process of doing so, 4 electrons are accepted by oxygen. So you can go for 4 there directly. That's up to you guys. Okay, see if that makes sense. So yeah, basically when you try to balance this equation with the one below, you have to multiply a 2 with this, because 2 times 2 is 4, and then this balances, or else either equation wouldn't match. That is the origin of this 2 over here. Okay, so this should be a minus 4. F is the Faraday constant at 96,500, and the E cell for this equation is given as plus 2.01 volts. Okay, so we're getting a value of minus 7.75860 joules per mole. Now to convert this to kilojoule per mole, you have to divide by 1000. You get a value of 775.8 or 776 kilojoule per mole to 3SF. Yeah, hopefully that's clear now, guys. Moving on to 4. Okay, so for 4, the 3d orbitals in an isolated Fe2 plus ion are degenerate, which means having the same energy level, right? So iron is 26 actually. You can see that from the periodic table. So, and it's actually a 4D. Here you go. It's 4D6 probably. Yeah, iron is 26. That's 1, 2, 3, 4, 5, 6. Okay, so 4D6 it is. So how do we do that? 1, 2, 3, 4, 5, 6. Okay. Now, after splitting, we know that in an octahedral complex, it's going to split into two divisions. Like two orbitals are going to a higher energy level, while three orbitals are going to go to the lower energy level. And x, y, z, and xz go to the lower ones, and x square, y square, and z square goes to the upper one. So now the new configuration will be. Oh, by the way, this is an Fe2 plus ion, so it's going to have 2 electrons less, right? But you must be wondering, why did I write 6 here? Because it actually has a 4s orbital, right? The electrons are removed from the 4s orbital first. Be sure to remember that, okay? Because it's actually 4s to 4d6. Anyway, 1, 2, 3, 4, 5, 6. Now this is the um, new organization. Okay. So this is the marking, these were the marking points. 5d orbitals in the isolated Fe2 plus ion of same energy, splitting 2 higher and 3 lower d orbitals. Energy of non-degenerate d orbitals in the complex more than the degenerate d orbitals in isolated ion. What do they mean by this? Energy of the non-degenerate d orbitals in the complex are more than the degenerate d orbitals in isolated ion. Do they mean both? I just need to check for a bit. No, basically it's like this. It is like this. Basically, a few get higher energy levels while the others get low energy levels. But for an isolated ion, this is true in a sense that basically this is the diagram. Do you want me to show you? So here you go. This is the isolated atom basically, and this is the complex. But when it splits, it divides into two parts. So probably, like I tried to draw this figure, okay, but this isn't isolated. So at first, when it's isolated, it should basically have very low energy, and then it gets higher energy, which is split into two parts. They meant that basically. Okay, this is the free metal ion. Okay, probably this is what they meant. So yeah, the mark scheme actually says, um, you know, it says that energy of non-degenerate d orbitals in the complex more than the degenerate d orbitals in isolated ion. So yeah, that's perfect. That's fine. It's okay. So since this was an isolated ion, I'm just gonna make it go lower, and yeah, and we are missing a step in between basically. Do you guys understand? The step in between is missing, but that's okay. That's totally fine with us. It's okay. Great. I haven't seen this in the mark scheme before. This is the first time I'm seeing this, by the way. So bipyridine, bi-P is a bidentate ligand. What is meant by bidentate ligand? Okay, so we know that the ligand has a lone pair to form a dative covalent bond, but a bidentate has two. So it's basically a species that donates or uses two lone pairs, okay, that's one point, to form dative covalent bonds or dative or coordinate bonds to the central metal to uh, metal atom or metal ion, okay, or transition metal, transition element, okay, or just metal. Anything works, honestly. Hopefully that makes sense. This is the latest definition. We follow this. Okay, so I want to make a video on transition metals, by the way. A lot of you have requested that. I'll try to do that before your A levels, and one on spectroscopy. Also, if you guys like the chemistry content, please subscribe to the channel. I mean, if you want more paper 4, please comment below. Paper 4 videos get less reach comparatively. That's why I haven't done them much. But if you do guys want more of this, please do let me know. So if you have 3 bidentate ligands in an octahedral complex, you can only form optic isomers, nothing else, okay? So let's do this. I'm gonna copy this. Here you go. So mirror images, okay? So we're gonna use this to represent by P. So mirror images, right? So this is one way to do it. Okay, they're mirror images of each other. This looks good. Here you go, optic isomers. So optical isomerism. By the way, this isn't the only way you could draw it. Like you could also draw this over here, okay? You could draw this one over here, and like, let me show you. You could also do this, okay? You could draw this over here and this here, okay? These are also optical isomers. In the mark scheme you only have one answer, but that doesn't mean that's the only one, okay? But I'm just gonna follow the mark scheme over here so that it's easier for you guys to follow. Stirring electrode potentials can be used to compare the stability of different complex ions for a given transition element. Use the relevant data from table 4.1 to state which ion complex is the hardest to reduce. Okay, so the lower the reaction potential, the harder it is to reduce. So clearly it's this cyanide complex, since it has a reduction potential 0.36 only, right? So let's write this. It's actually FeCN 6 3 minus. And why? This is because this complex does not want to go to the right hand side. The reduction potential means how easily it will go to the right. Since it's so low, it wants to stay on the left hand side. Do you guys get what I mean? A lower reduction potential means that the equilibrium lies more to the left compared to the right. Okay, so that's the answer. The equilibrium lies most to the left. Okay, or it has the lowest E cell value. Okay, the lowest reduction potential. Anything works, honestly. So the ligand pyridine consists of two pyridine rings. Pyridine C5H5N and benzene have similar planar cyclic structures. By reference to the hybridization of the carbon atoms and the nitrogen atoms and orbital overlaps suggest how the sigma and pi bonds are formed in a pyridine molecule. Okay, so this is pyridine basically, and just instead of carbon over there, we actually have one nitrogen atom, right? So we have 5 carbons and 1 nitrogen. So this ring means there's like 3 double bonds over here. So the structure is kind of like this, or you could draw it like this. Either works. Either one works. Same resonance. So the nitrogen has actually 2 bond pairs and 1 lone pair here actually, right? So 2 bond pairs and 1 lone pair, 2 plus 1. That means it has a value of 3, the hybridization number. So it's actually sp2 hybridized. Okay. So the nitrogen is sp2 hybridized, and so is the carbon. The carbon is also sp2 hybridized. We know that from benzene. So they do have pi bonds, right? Now, where are the sigma bonds formed? Basically, this nitrogen does not have any hydrogen with it, but there are hydrogens over here. Hydrogen here, hydrogen here, hydrogen here, here. So where are the sigma bonds located actually? So the sigma bonds are formed by head to head, right? End on end overlapping. End on end overlapping, that's the term they used. Okay, so sigma bonds are formed by end on end overlapping or overlap, you could say. End on end overlap orbitals. Weird wording. Between whom exactly? Either CH or CC or CN. And that's one point. And what about the other point? Pi bonds are formed by sideways overlap of p orbitals. Sideways overlap of p orbitals between, we don't have a lot of options here. It's only CC or CN over here because there are no pi bonds between CH. Okay, very important question, guys. Very important. So they wanted to know the hybridization and how pi and sigma bonds are formed basically. Sideways overlapping for pi and end on end overlapping for sigma. Pyridine reacts with chlorine in the presence of AlCl3. So we know that this is a halogenation reaction by electrophilic substitution. We know this. You've learned this. So let's draw the mechanism, shall we? So the first step is attack by the electrophile on the nucleophile. Although the convention is to draw arrows from nucleophiles to electrophiles, but the electrophile is actually attacking here. Okay, that's why it's called electrophilic substitution. So let's draw the intermediate. So I'm gonna copy this exactly. It's just that we are going to draw the intermediate with this chlorine atom and hydrogen atom partially over here, and we're gonna get the lunar structure. Make sure your, you know, ring passes through all of these like this, all 5 carbons except one over here. It can't touch that spot. You have to give a plus sign over here, and there will be heterolytic fission of this bond, and it will enter the ring towards the positive charge. See if you guys can follow. Is that fine? Okay, so let's go to the last step. We are going to get our product. I draw so bad. Okay, so we are going to get our product as this compound. Oh, my bad. I should have drawn a nitrogen here. One sec, let me fix this. Here you go. Okay, so we get the ring back and we have the chlorine over here. And as a byproduct, we are going to get an H plus, okay? Perfect answer. So that's that. This is a 3-chloropyridine, yeah? Because this is carbon 1, 2, and 3. 3-chloropyridine. This one. Okay. Moving on to 5. We only have 3 questions left now. 5, 6, and 7. Let's finish this. It's not much. Okay. So compare the acidities of benzoic acid, phenyl methanol, and phenol. So phenyl methanol is actually an aliphatic alcohol. Phenol is okay, it's all right, and benzoic acid is actually a carboxylic acid. So clearly carboxylic acid will be the strongest, right? So benzoic acid is the strongest, and the aliphatic alcohol, which is phenyl methanol, will be the weakest, and phenol is in the middle because it's an intermediate between an alcohol, an aliphatic alcohol, and a carboxylic acid. It's basically an aromatic alcohol, which is why the benzene ring, weakens the OH bond, so it facilitates the removal of the H plus, right? So let's write this. So I'm going to talk about benzoic acid first. So in benzoic acid, why is it so strong? This is benzoic acid. You know about it, right? This is benzoic acid. So in benzoic acid, we have the CO group, right? So the carbonyl actually weakens the OH bond really, like it helps in weakening the bond. So in benzoic acid, the negative inductive effect of CO weakens the OH bond. Okay, that's great. Or you could use alternate wording. You could say that basically the carboxylate ion is stabilized due to delocalization. Okay, so you could say that due to delocalization of the negative charge by the carbonyl group, or by the two oxygens present there, the carboxylate ion is stabilized. So this point goes in favor of carboxylic acid, benzoic acid. They're basically talking about this scenario over here. So this negative charge over here is actually stabilized there. Okay, it forms a resonance structure. And what about the other ones? So basically, in phenol, what's up with phenol? In phenol, the lone pair on oxygen is delocalized in the benzene ring, right? Delocalized into the ring, and what happens? The OH bond is weakened. Oh, okay, so yeah, that's great. On the other hand, I'm gonna write the one for phenyl methanol here. In phenyl methanol, We know that alkyl groups have positive inductive effect, right? So it actually makes the situation worse. Positive inductive effect of CH2 group strengthens, right? Strengthens the OH bond. So it's harder to lose the H plus. Do you guys get it? So yeah, you should be following this mark scheme. This is the latest answer to the guides for acidity. You should also learn the one for the comparison of basicity, by the way, okay? So let's do this. We know that all of these are acidic. So benzoic acid is acidic enough to react with all of them. Phenol is acidic enough to react with NaOH and Na, but not Na2CO3. On the other hand, phenyl methanol can only react with active metals, but not these. Very common question, okay? So they want us to write this reaction with PCl5 and SOCl2. So we know that we are going to get acyl chlorides, but we want the byproducts, okay? So here in PCl5, this occurs at room temperature, both of them actually. We get phosphoryl chloride, POCl3, and the byproduct as HCl. Here, with thionyl chloride, we're going to get sulfur dioxide gas and HCl, okay? Use the answer to suggest why it is easier to isolate in pure form. Oh my god, I was just about to say this. Like, uh, but I actually had second thoughts. I was about to say that you've seen this reaction from a scheme, right? In reactions of alcohol with alkyl halides. So I always tell my students that the second one is much better than the first, mainly because the products are all gaseous, right? SO2 and HCl. So they're going to be removed from the apparatus very easily, and we're going to get a pure form, okay, of the product. But in the first one, actually, POCl3 is aqueous in nature, okay? So it will actually act as an impurity, okay? So this is very important for A students as well as A2 students. Very important, guys. So all the byproducts in reaction 2, basically, they're talking about SO2 and HCl are gaseous, okay? Or you could say that no liquid byproducts formed, yeah? No liquid byproducts formed. Moving moving on. Excuse me. So benzoyl chloride is hydrolyzed by water at room temperature to form benzoic acid. Okay, so this is hydrolysis of acyl chlorides to form carboxylic acid. So this is a new mechanism that has been added this time onwards. It's called addition elimination. You can see this in my A2 organic in 40 minutes video if you haven't studied this already. But since this has been added in 2022, it is bound to show up in every question from now on, every variant, yeah? So let's begin, shall we? So this is the electropositive carbon atom. This is the electronegative oxygen atom. So the first step is actually attack by the nucleophile water on the electropositive carbon atom, but this carbon can't have 5 bonds, right? So this bond will break immediately like this. Okay, there you go. Is that fine? Now in the next step, the intermediate is the complicated part. Okay, now this is the tricky part. So you have C6H5 over here. They opted to show it as C6H5 because there was probably no space, I'm guessing, but it's okay. So this is our C over here. Now you have O on one end, chlorine on one end, and this OH2 or this H2 on the other end. So now we have to work with this. Okay, so I'll teach you what happens actually. So this oxygen has a negative charge, right? Because it took the electron from carbon, and carbon actually took an electron from oxygen. So our oxygen has a positive charge currently. You guys need to understand that. Okay, do you get the basics? Carbon took it from, okay, so oxygen took it from carbon, so carbon has a deficit. Now carbon took it from the oxygen from water. Now water has a deficit. Now what? So basically what's going to happen is um this double bond will reform again, okay, but this carbon will have 5 bonds then, right? So to prevent that from happening, uh, this, you know, there will be heterolytic fission of this bond, okay? So chlorine will become chloride. And now, oxygen lost its excess electron and carbon got its electron back, so everyone's happy. But what about that oxygen that's positive? It's not happy right now, right? So basically what's gonna happen is, I don't know why, but I've seen in the May June 2022 4-2 variant as well, or the March Feb 2024 variant, that they don't really draw this arrow though. They don't draw this arrow, but this is what actually happens, okay? Because we want this oxygen to get the electron back, and H is released as H plus, and here we have Cl minus, which reform to make hydrogen chloride gas. But I don't know why they don't show it, okay? But I personally feel like you guys should, because it was in the course book, by the way, but this wasn't shown in the mark scheme, okay? Just letting you guys know. So what's the mechanism? It's addition, elimination. Okay, great. Super important for May June 2023, okay? Moving on. Acid chlorides react with sodium carboxylates to form acid anhydrides, that's shown, okay? That's basically an ether bond. The condensation polymers, polyanhydride and polyester, formed by similar methods. The repeat unit for polyanhydride is shown, okay? Suggest the two monomers used. Pretty simple, straightforward. So the acid anhydride actually has an R group on each of its ends. And this is basically polyanhydride and polyester are formed by similar methods. Okay. Interesting question. Polyanhydrides and polyesters. So we know that for ester bonds, we need alcohol and carboxylic acid, or alcohol and acyl chloride, right? So for polyanhydrides, we actually need an acyl chloride and a sodium carboxylate, essentially a sodium salt, right? So that's what we needed to figure out. So let's try to decipher this. So I'm essentially looking for this bond that we've created over here, because this was not there, right? This has been created newly. So basically, if you do break this bond, it's like a glycosidic linkage in a starch. If you had AS bio, that's the position where the bond was made actually, okay? So if you guys are, if you guys look at it carefully, we can find the location of the bond. It's just over here. Do you guys get what I mean? So this is one of the monomers. On the other hand, this part over here, this part over here, okay, this over here is another monomer, because the O would have been here, okay? So let's draw it. So one of them will have chlorine, that's the acyl chloride, and the other will have, an ONA. It will basically be a sodium salt, okay? So basically, let's do this. So we have the C over here, the acyl. We don't know actually, but I'm just gonna start drawing. I'm just gonna copy paste the upper part over here. Oxygen, so we have a CH2, 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 back to oxygen. Then I have this benzene ring again, okay, followed by this part over here, okay. And on this side I actually have this CO over here, this part over here, followed by a CH2, CH2, CH2. Do you guys get it? CH2, CH2, CH2. I'm just copying that, okay? followed by, yeah, this over here. Now the choice about acyl chlorides. Okay, so if you choose to make this the acyl chloride, then you've got to make this the sodium salt per se. Okay, it's not rocket science. And if you choose to make this the sodium salt, you just make this the acyl chloride. You had both options, honestly, because we didn't know which one was the acyl chloride initially. Okay, so you had both options. That's totally up to you. Now they are biodegradable, just like polyesters. How? Mainly by hydrolysis. Okay, hydrolysis is the reaction, or you could describe it as heating in dilute acid or alkali. Okay, perfect. Guys, we have made it to the sixth question. Let's do this. We're almost done. I'm just gonna take 20 more minutes. So, so what is a racemic mixture? This has also been added to the 2022 syllabus. It is basically a mixture, okay, containing equal amounts of each optical isomer. Very important. So it has each enantiomer. So the net effect of plane polarized light will be 0, because one will make it move clockwise, the other will make it move anti-clockwise. But since they're equimolar, that is why the net amount is 0. So this is asparagine. It's an amino acid, and it contains a chiral carbon atom and displays stereoisomerism. Perfect. So this is our chiral carbon. Yeah. So let's look at the carbon NMR and proton NMR. Pretty simple. So this is an environment, these two hydrogens, and it's going to be isolated. Let's call this A. Okay, clearly, because if you're attached to an electronegative atom like nitrogen or oxygen, you know that you get an isolated peak. It's a singlet. Okay, so this one is also another unique environment. This proton over here. Okay, I'm gonna call this B. We have none like it. And if you want to know about the peak, if you look at adjacent carbons, the one on the left doesn't have a proton, the one on the right has a proton attached to it. So this will actually be a doublet. B is a doublet, A is a singlet. Now let's move on to this one. This proton over here, this CH, this one actually has two protons adjacent to it. Okay, so this will actually be a triplet. I am looking at this, by the way. My environment has two protons. I'm ignoring the nitrogen because it's electronegative. This is also another environment, by the way. It is an NH2, just like the orange one. However, it's not the same NH2, right? It's a different NH2. It also has a very high chemical shift, but it's not the same as the orange one. So it's environment D. And last but not least, I have this OH, our old body OH. This is capital E, which is a singlet as well, because it's connected to an electronegative atom. So I'm gonna do a quick review. A, D, and E, these are singlets because they're connected to electronegative atoms. B is actually a doublet since the adjacent carbon has one hydrogen. C is actually a C is triplet because the adjacent carbon has two hydrogens. By the way, who has the highest chemical shift? Probably E or A, followed by D, followed by C, and then B, because C is closer to the electronegative atom than B. Okay, so how many peaks do I get for the carbon, for the proton NMR? The answer is actually 5. Could I clarify? Okay, do we have any NMR stuff later on? We actually don't, but I don't want to erase this, honestly. Okay, I'll just keep this on the side. Okay, moving on to carbon NMR. Fine. So look at this carbon. This carbon is unique. It has one NH2 on one end, while a CH2 on the other end. So it's unique, yeah? So this CH2 is unique, the carbon over here, because we don't have any other CH2s. Okay. Now this carbon is unique because it has a COH attached to it and an H2 attached to it. That's unique, right? So that's C. And this carbon is also unique because it might be a CO just like A. However, A had NH2 attached to it, but this D has OH attached to it. So in total, we have 4 carbon peaks. Get it? So since you don't have access to the data booklet anymore and the values of the chemical shifts, I don't think you'll be asked to read those spectrums anymore. So I guess it's easier for you now. You'll just be facing questions like these. So yeah, that makes it easy, honestly. So what's the isoelectric pH or point? It is the pH, capital to an amino acid. It is the pH at which an amino acid exists as a Zwitterion. So next question, what is a Zwitterion? Basically something that has no overall charge. So you could also say it is the pH at which an amino acid has no overall charge. Okay, both work. So I'm going to teach you something, never forget. At pHs below the isoelectric point, the amino acid will have a positive charge, and at pHs above it, it will have a negative charge. So the isoelectric point is actually 5.4. Now we're asked to draw it at 1. So at the isoelectric point, it's basically like this. This NH2 will, okay, that's the R group. This is the R group. You guys get that, right? This is the R group. So this NH2 will basically turn into NH3 plus, and this COOH will turn into COO minus. That's the situation at the, isoelectric point. Now, what happens at the low pH of 1.0? We have a large excess of H plus, right? So that H plus will actually come over here. As a result, instead of CO minus, it will turn into COH. Also, we have an extra NH2 over here, right? This will turn into NH3 plus. So the R groups are also interacting at very low or very high pHs. Please do remember that, okay? Because you have a large amount of H plus, the CO minus will attract it, and you know that NH2, that's a Bronsted-Lowry base actually, so it will actually, also interact with the extra H plus. It will try to accept the H plus, and it exerts its buffering action. Okay, so logically that's what's supposed to happen, but apparently in the mark scheme they did not show that. So they just went for this. This is asparagine. They just went for NH3 plus. Okay, COOH. This turned into from CO minus to COH, and on this side they kept it as, they actually kept it as NH2. So if they don't mention anything, I don't think we should take hold of the reins and make decisions over here. But honestly speaking, 1 is a very low pH, so that NH2 as well should have interacted. That's my personal opinion. Okay, to turn into NH3 plus, but it's fine though. It's okay. You might lose 1 mark here and there, but that won't really make a huge difference. Okay. Now it can polymerize to form polyasparagine. So we know that the R group does not take part in this. It's only the main COH, right? It's the main COH. We know that it's like this: R COH in H2H, right? So let's do this. So this is the R group over here. I'm telling you continuously. Okay, let's do this. So we have a C over here. So we are going to get the CONH bond in. We are going to show 2 repeat units, right? Okay. So this is my hydrogen over here, and this is the R group. What's the R group? CH2 CONH2. Okay. CH2 CONH2 CONH2. Okay. And of course we have nitrogen over here, which is also ready to form a bond, but we're going to keep that open-ended. Okay. On the other hand, on this side we also have another CO with the R group again, CH2 CONH2. Okay, H down here, and CO, and yeah, we keep it open-ended. Okay, that's how you do it. See if you guys understood. Is that fine? That's 2 repetions. And if they wanted a dipeptide, you would just do this, by the way. But they wanted a polymer with 2 repetions. That's why we have to keep it open-ended. Yeah. Isotopic point of lysine is 9.8. Okay, great. So at isotopic point, it's basically like CO minus and NH3 plus. Okay. So a mixture of dipeptide, lys and ASN, asparagine, yeah, is analyzed by electrophoresis using a buffer of 5. The results obtained are shown here. Awesome. So guys, in this mixture we see 3 dots. So basically what happens is one is lys asparagine, one is asparagine, and one is lysine, because the buffer actually causes hydrolysis of the bond, but not all of it is hydrolyzed. So we see all 3, and clearly all of them are moving towards the cathode. That means they are positively charged. Okay, so how do we deal with this? Okay, so the pH is at 5. Okay, the pH is currently at 5. Now we know that the isotopic pH of ASN, asparagine, is actually 5.4. It's 5.4 iso. And for lysine, it's apparently 9.8. So yeah, I was talking about this. Let's do this. So I told you that below the isotopic pH, if you have a pH below the isotopic point, then the amino acid has a positive charge, no doubt about that. Now if you go to the extremes of it, like compare pH 5 to pH 9.8, clearly, you know, um, it's very low, right, compared to 9.8. Okay, so this is 9.8, and what was the isotopic point of 5.4? This is 5.4 over here. This is the pH of the buffer. So this is a very close proximity, right? So we can't really say that asparagine is positively charged. It might still exist as a Zwitterion. Do you get what I mean? As a result, E or asparagine doesn't really move that much because it is almost neutral. Because 5 isn't very low compared to 5.4, so maybe it doesn't turn into a positive charge and from the Zwitterion. On the other hand, 5 is much lower than 9.8, so clearly lysine will turn into a positive ion. And what about lys and asparagine, the dipeptide? So this will stay neutral, but this one will be positive. So this one is positive and this one is neutral. As a result, asparagine doesn't move that much because it's neutral. Now between lysine and lysine asparagine, which one will move more? When the charge is the same, you need to look at the MR. Since lysine has a lower MR compared to the dipeptide, clearly G is lysine. Does that make sense? Hopefully I could clarify. Still, let me know, guys, if you do need any help. All right, so let's explain. So lysine and lysine asparagine are positively charged, and you do not need to write N, but you could write any one, but still I'm writing N. And asparagine is nearly, okay, this was optional, nearly uncharged. Important. On the other hand, the other point is comparison between F and G. So lys asparagine has the highest MR, okay, which is why it moves a bit less than lysine only. Get it? Okay, then hopefully I could clarify. Moving on to F, we need to know the stationary phase of thin layer chromatography and gas liquid. Please memorize these. So for thin layer chromatography, it's actually silica or alumina. So you could go for silica on solid support. Okay. Or an alternate option was alumina, which is basically aluminium oxide. Anyone works really. And for gas liquid chromatography, it's actually an inert gas, typically nitrogen. Okay, for example, nitrogen. Here you go. You need to have this memorized. And for paper chromatography, the stationary phase is the water attached to the cellulose, right? Hydrogen bonded to the cellulose, and the mobile phase is the solvent. So an unknown amino acid is analyzed using thin layer chromatography. 2 chromatographs of the unknown amino acid and 4 reference amino acids PQRs are obtained using 2 different solvents. Okay. Identify the amino acid, justify answer. So clearly, our unknown amino acid, it matches with Q or S, basically, the solubility in this solvent. So our potential candidates are Q or S. And in this solvent, in solvent 2, this isn't two-way, by the way. In this one, our unknown amino acid matches in solubility in this solvent with R or S. Okay. So we are basically looking for the common one, which happens to be S, alright, because it matched in both cases. That's why we clear out all our confusions. So clearly it's S. The reason being the RF, right, the retardation factor, is the same in both solvents, is the same as the unknown, this unknown amino acid. Oh, we are looking for the unknown amino acids basically with known ones. S is the known one. Okay, with as the unknown amino acid in both solvents. Okay, that's great. So yeah, 2 amino acids might have the same solubility in one solvent, but to clarify it, we can check it in more than one solvent. Yeah. So G, a mixture containing 3 organic compounds is analyzed by gas chromatography and mass spectrometry. The gas chromatography is shown. Great. So the shorter the retention time, the faster it has passed through, and that means it has less interaction with the stationary phase. Okay. The area underneath each peak is proportional to the mass of the respective compound in the mixture. You could actually do one gas chromatography question from ON 2018 if I'm not wrong. It had questions in both variants. The concentration of K in the mixture is this much. Calculate the concentration in mole per dm cube of L. Okay. So basically, using this information, we can find something out. Let's do this. So area is proportional to the mass of the respective compound. Okay, so let's find out the mass of K, shall we? How much is it? 44 divided by 44 plus 8 plus 58, right? So let's do this. One sec. Let me get my calculator. 110, right? I'm making a mistake. 44 plus 58 plus 8. 110. The area is proportional to the mass of the rest. Oh, it's just proportional to that, right? To the mass. So I don't think we need to do a ratio in the first place. Probably not. So okay, we don't need to do this, my bad. So they've said that the area is proportional to the mass. So basically, MR of L is 116. Oh, okay. So this over here, I totally missed this. we need to convert to mole per dm cube later on. Okay, so we find it in gram per dm cube followed by conversion to mole per dm cube. That's great. So okay, that's fine. How do we do this? Basically, the area of K, we are going to use K. Area is proportional to mass, right? And we know the concentration of K. So let's do this. So if you multiply 44 times, 5.5 to 10 power minus 2, you're going to get a certain answer. So it's basically a unitary method. Do you get what I mean? For example, we know that area is proportional to mass, okay, which is in gram per dm cube. So can we write this, that area by mass is actually a constant? Do you get what happened? So we can write that area of K by mass of K is equal to area of L by mass of L. Essentially, that is what we're doing. So if I rearrange this, mass of L is equal to area of L divided by area of K times mass of K. So mass of L is equal to, what's the area of L? 58 by 44. Okay, so 58 by 44, I got that info from the table, times the mass of K, which happens to be 5.52 grams into 10 power minus 2 gram per dm cube. Okay, in 1 dm cube. Okay, so let's try doing this. So that's 58 by 44 times 0.052. We get an answer of, yeah, wait, 0552, my bad, I was using, yeah, 0552, my bad. So 58 by 44 times 0.0552. Yeah, now it matches as 0.0727. Okay, that's great. So I'm getting a value of 0.07276, which is basically 7.28 rounded off, right? 7.28 into 10 to the power minus 2 grams. Okay, per dm cube, of course. Now we know that, you know, moles equals to mass by mR. So the concentration is basically equal to 7.28 into 10 to the power minus 2 divided by 116 basically. So we are getting an answer of 6.27 into 10 to the power minus 4. Okay, 6.27 into 10 to the power minus 4. That's how you do it. Sorry about the delay. Let's move on to the last question then. We are almost done. Last question, question number 7. So I actually have this done. Let's still see this. Okay, let me erase it and do it again. It's fine. It's pretty easy. Okay. Oh, I did not erase this. Yeah. Okay. So guys, what are we seeing? Procaine. It's an anesthetic and medicine. We read about it in pharmacology basically. So it can be synthesized from methyl benzene in 5 steps. Great. So steps 1 and 2. Basically, you guys need to be careful about something in steps 1 and 2. Basically, we know that CH3 is orthopara directing, not meta. That means it directs to 2, 4, or 6 positions. So clearly we have nitrated the benzene ring. So if you perform nitration first, You can either get it here or here. But if you actually oxidize the CH3 to COOH first, then it turns into a metadating group. So the NO2 could only go here. Do you guys understand what I mean? But clearly, in our answer, we know that it's in the fourth position. So clearly, we are not supposed to oxidize it first. We need to nitrate it followed by oxidation. That's the thing that you guys need to understand, okay? Very common question that they test. Name all the functional groups present in procaine. So in procaine, this compound over here, clearly we have the aryl group. We have a phenylamine. If the NH2 is connected to the benzene ring, you have to write phenylamine. This one is the NH2 below. Then we have the COO group, which is basically an ester. Okay. We also have an N connected to an N connected to these three, CH2 CH3 CH2 CH3 both, and then here CH2 CH2. So we don't have the NH over here, but this is essentially an amine. Okay, it's a tertiary amine to be exact. It's an amine. Okay, the amine was hard to get. It's a tertiary amine, but yeah, it's not aryl here. Aryl isn't accepted anymore, by the way. It's kind of like alkane now. It's not a functional group. State the number of carbons in procaine. So sp3 hybridized carbons. We know that for sp3 hybridization, for sp hybridization, we need a carbon which has triple bonds, like what's it called, alkynes. So there are 0 sp carbons. For sp2, we know that the carbons in benzene, these 6, 1, 2, 3, 4, 5, 6, these are all sp2, and any carbon that has a double bond, this one is sp2 hybridized. So in total, that's 6 plus 1, which is 7. Now what about the other ones? So this carbon 1, 2, 3, 4 times 2. So this 1, 2 times 2, 4, 5, 6. We have 6 sp3 carbons in total. Basically, these 4 inside this bracket, if you have 4 bonds, 4 single bonds, you're an sp3 carbon, okay? Now the proton NMR of procaine is dissolved in D2O. D2O is heavy water, you guys know of that. So if you dissolve the substance in heavy water, the labile proton actually goes away in COH, OH, or NH. Okay, so predict the number of peaks observed. So usually in procaine, how many proton peaks are we supposed to see? Think about it logically. So check this. I'm going to draw the compound. Proton NMR, okay? So basically, this CH3 and this CH3, they're the same environment basically, okay? Because it's the same, CH2 and this CH2, they're the same. Because if you go to the left, like if you go one step, you see a nitrogen. If you go to the other side, you're gonna see a CH3, okay? Moving on, this CH2 is unique. There is no one like it exactly. This CH2 is also unique. There is nobody like it. And in this benzene ring, right? So in this benzene ring, all the hydrogens are in one specific environment. Okay, so we are just gonna call that E. Whoa. We are going to call this E, all the hydrogens here. This is group E. And this NH2, it's actually F. So how many peaks do we see for procaine? It's actually 6 peaks, yeah? So that's 6 peaks. Hopefully you guys could understand. 1, 2, 3, 4, 5, 6. About heavy water though. Like heavy water actually, like let me show you something from the syllabus. Where is H2 organic? I am confused about something over here. Wait up, wait up, wait up. Yeah, so describe the identification of OH and NH protons by proton exchange using D2O. So this proton from NH2 isn't being exchanged actually. If it was OH, it would disappear for sure. But is it a phenylamine? Is that why it isn't being replaced? I'm not exactly sure, but if you dissolve it in a solvent, you would get 6 peaks. But with the addition of D2O, it wouldn't really disappear here apparently. So maybe one hydrogen was switched, okay? Because D is actually NMR inactive, so you wouldn't get a peak for that if this was converted to ND2, okay? But I guess only either one hydrogen is exchanged or the exchange doesn't happen in the first place. 5? Yes, 6. Okay, I will get back to you on this. If I do find something out, I will mention down below in the comment section. But for now, for sure that it has 6 peaks. Clearly A, B, C, D, and E for the benzene ring. All protons in a benzene ring are always in the same environment, and F for amine. But I just need to check why this hasn't been, exchanged completely. I'll let you know in the comments. Okay. So state why Procaine can act as a base. Oh, okay, okay. So basically, my bad, my bad. Um, Here maybe what happens is this NH2 does act as a proton acceptor. The D comes in here, okay, but it isn't exchanged completely. That's what happened. Probably that's what happened. So you do still have hydrogens over there, okay. A dative covalent bond is formed with the heavy with deuterium, but we don't lose the NH2. That is probably the answer why we don't lose it, okay. So why is procaine a base? Because the lone pair, right? The lone pair on nitrogen can accept a proton. So yeah guys, that is probably the reason, but if I still do have updates, I'm gonna let you know. Let's end it then. So methyl benzene, yeah, I was talking about this a bit before. So you cannot oxidize first, you have to nitrate it first followed by oxidation, or else it would go to the meta position. Okay, so for nitration what do we need? We need concentrated HNO3 nitric acid and concentrated sulfuric acid. You guys know that. And the temperature from 25 to 60 degrees Celsius. They did not mention that for some reason. And for oxidation, we need hot alkaline. Go for alkaline. Alkaline is the latest mark scheme. They used acidified before, but now in the syllabus it's mentioned alkaline. Hot alkaline KMNO4 followed by addition of H plus. Okay, that's very important. Procaine is synthesized in 3 steps from X. Okay, so what do they want? So at first, we get the acyl chloride. Great. So they want the reagents for step 4 and 5. So we get the acyl chloride, and in this step, and something reacts with the acyl chloride. Basically, COCl reacts with something else. So we know that acyl chlorides can react with amines to form amides, given that the amine does have a hydrogen, only with primary or secondary, by the way. Ammonia, primary or secondary, not tertiary, and with alcohols to form an ester. Clearly, this is an ester bond. So, if you hydrolyze the ester bond here, you can get the product. So, we actually added this compound over here, CH2, CH2, N, CH2, CH3 to this thing. This is the compound, okay? We actually added this alcohol and amine, this intermediate thing. Okay, so we actually added this HO CH2, CH2, N, CH2, CH3, 2. Okay. And for step 5, what did we do exactly? Oh, we reduced the nitrate to an amine. So we use tin and concentrated HCl, yeah? Tin and HCl, concentrated HCl. You have to mention that. Tin and concentrated HCl. And of course, heat under reflux. Okay. Last one. Explain what is partition coefficient. Really important definition. It is the ratio of the concentration of a solute the ratio of the concentration of a solute in two solvents. Okay, you get 1 mark for that, and then you need to mention at equilibrium. This is very, very important. Okay, that's the second mark. Now we had a math on partition coefficient. So the partition coefficient of procaine between octane 1-ol and water is 1.77. So procaine in water and in aqueous conditions and in octane 1-ol. So remember the trick. The name that they mentioned first goes to the numerator. So octane 1-ol is the numerator. Octane 1-ol and water are immiscible. A solution containing 0.5 grams of procaine in 75 cm cube of water is shaken with 50 cm cube of octane 1-ol. Okay, so initially the procaine was in water. Now it's shaken with octane 1-ol. So some procaine will enter octane 1-ol from the water. Okay, some procaine will enter octane 1-ol from water. So this is it. So let's write this. So KPC is equal to, I told you, it's basically procaine in octane 1-ol divided by procaine aqueous in water, basically, yeah. So the value of KPC is 1.77, and initially there's nothing in procaine, right? It's 0. So from 0 it will turn into X. So that's X divided by 50 cm cube of octane 1-ol. On the other hand, in water we had 0.500. Now it will turn into 0.500 minus 6. Some will be deducted from it. So 0.500 minus 6 divided by how many cm cube? 75 cm cube of water. So that's the working. Okay, do you guys get it? So if you perform the reciprocal, what's going to happen exactly? 1.77 is equal to, like, 75 is going to go to the numerator. So 75 by 50. 75 by 50 gives you an answer of 1.5. Do you get what happened? 75 into x by 50 divided by 0.5 minus x. So 75 by 50. So that's 1.5x divided by 0.5 minus x, followed by 0.5 times 1.77. 0.5 times 1.77, which is 0.855. So 0.885, sorry, 0.885 minus 1.77x is equal to 1.5x. So 1.5 plus 1.77 to 3.27. So that's 0.885 is equal to 3.27x. So the value of x is ultimately 0.271. Awesome. So guys, that is all. So this is why I don't like doing paper 4 questions, because it takes a long time. It's actually really hard. Like, out of all the papers I've done, bio paper 4s and chemistry paper 4s are really hard to do, but it doesn't get that much reach comparatively. So please let me know if you've enjoyed the video, and if you do want more papers like this, I will solve them. I will solve paper 4 too when I get the free time. I will solve the major 2020 and 2022 papers if I do get the free time. But please remember to subscribe to the channel. Thank you. So I'm going to link the paper for um, you know, June 2022, paper 4.2 up here when I solve that. And I'm gonna link the paper for March 2022, paper 4.2 down here, and the playlist for Chem paper 4 up here. And remember to hit the subscribe button. See you guys.